Hello, everybody. This is Antonios from Hopsworks. And in this webinar, we're going to explore the high availability characteristics of Hopsworks feature store. So the agenda for this webinar is we're going to go through very briefly what is a feature store and why do you need the high availability. Then we're going to see the high availability characteristics of Hopsworks in the different aspects. And then we're going to go one step further and explore the multi-region high availability of Hopsworks. So I assume that some of the audience here are not very familiar with feature stores. So I will give a very brief primer of what is a feature store. And before that one, I need to explain what are features. So features are data for AI, and it's some measurable property that's used as an input for a machine learning model. Now, why do we need a feature store? Because managing data is a very complicated process, and more specifically, if you want to query them efficiently. So this is where feature stores come into play, and this is where Hopsworks come into play. And Hopsworks is a multi-data platform. It has two databases: the online store and the offline store, and you can. Different teams can collaboratively curate the features, use them, and train the models. So this is a very brief introduction to a feature store. Now, I assume that if you haven't heard about machine learning before, and somebody told you what is a machine learning system, you would have some kind of this idea. So on the left, you will have some input data. You will do some feature engineering, you will clean them, you will transform them, and then you will train your model. And finally, you will make some predictions. And all this in your probably Jupyter in your notebook, or maybe in a Python program. The problem with this architecture is that although it's very simple and it's very easy to prototype, then the created features are not very easily reused. Modularity doesn't exist. If you want to have different use cases for online or offline, then you will have inconsistencies. Testing is difficult. And more importantly, separation of concerns is impossible. So in Hopsworks, we promote this, we call it FTI, Open Architecture. And FTI is the acronym of Feature Pipeline Training and Inference. And it's open because you can pick, to a great extent, you can pick your own tools, whether it's Python, whether it's PySpark. So we begin with a feature pipeline that takes us an input raw data. Then we continue to the training pipeline, which takes the feature that we have previously calculated in the feature engineering pipeline. We train the model, and then there is a different system for the inference pipeline, where you have your trained model and you serve it online and makes predictions. So it looks something like this. So three different pipelines, and they all communicate with each other through a common API. And this is the Hopsworks feature store. So as you can imagine, like the feature store is a keystone infrastructure in modern machine learning systems, and for that reason, it's very important that we maintain high availability. And as any other critical system in your organization, operational failure will incur most probably financial loss, reputational damage. It will hamper productivity, and in some cases, it will have some regulatory penalties. So now we have covered very, very briefly what is a feature store. For more details, I will forward you to our website. We have excellent material. We will go through the high availability characteristics of Hopsworks. So as we described earlier, Hopsworks is basically a dual data management system, a consistent dual data management system. And it consists of an offline store, which it's mainly intended for large volumes of data, historical data, and it's used for batch prediction, training for batch predictions. Then we have the online store, which is used to store features that are going to be used by interactive online applications, real-time applications with very low latency requirements. And in the middle of those two, we have the metadata layer, which stores some system metadata, file system metadata, and you can consider it as joining both offline and online store. So if you want to visualize it, it would look something like this. On the left-hand side, we have the different pipelines where you do your feature engineering, inside Hopsworks, or if you want, outside of Hopsworks. And then they end up in the online store or the offline store. And in the middle, you have the metadata layer, and then we do some predictions. We have the training pipeline. So I like to quote. I like to put up a quote from Leslie Lamport, which is basically the father of distributed systems, considered the father of distributed systems. And he said that the distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. So you would think, like, how is this? How does this relate to a feature store? Well, if you go to any modern website or like to any organization, you will most probably get greeted by a chatbot, and especially now with what we've seen, the advent of LLMs. The online store is very critical, and if something goes wrong there, then most probably you will notice it. So we saw the three layers of Hopsworks. So we will go into one of each one of those, and we will see the high availability characteristics, beginning with the metadata layer, because it's the link between the offline and the online store. So the metadata layer consists basically of the Hopsworks application server. Then it stores metadata information about the users, the credentials, cryptographic materials. Because internally in Hopsworks we use X509 certificates. Then they store feature group metadata information, feature user abstractions of feature groups. And then, of course, we have our distributed file system, which has information about the users, the groups, file permissions, logs, etc. So to store all this metadata, we use an in-memory database. It's called RonDB, which is a fork of NDB. It's basically a MySQL cluster with the NDB storage engine, which is a distributed in-memory database. It has very low latency. It is transactional, ACID compliant, and of course it has full SQL support. A RonDB cluster being distributed has many components. The first two are mandatory, and these are the management servers, which basically they don't perform any critical operation. It's only there for some maintenance tasks and also for joining the cluster together. And then we have the data nodes, which are basically the storage and query nodes. So all your data, they end up in data nodes. And then optionally, we have the API nodes, and we call them API nodes because they are basically clients to RonDB. And these can be MySQL server. It's your typical MySQL server, but instead of having the InnoDB storage engine, it uses the NDB storage engine. Then we have our own developed RESTful API server for querying the database using a REST interface. And finally, you can have multiple clients consuming the NDB API, which is a low-level API, which has bindings for Java, which is cluster J, and it's the one we use. But as far as I'm aware, it also has for JavaScript, for example. So typically, a RonDB cluster, it would look like this. So you would have, for high availability, you would have 2 management nodes. Then in the middle, you have the data nodes, and I will come later to the node groups. And then finally, at the bottom, you will have the clients of the cluster, which can be the MySQL server themselves, or it can be the REST API servers and cluster J applications. So let's discuss now about the fault tolerance of RonDB. I will not go into very much details because there are excellent resources in our website. But the building blocks of the high availability of RonDB, it's on node groups. You can think of it as shards. So all the data that you store in RonDB is partitioned and is replicated within the shard or within the node group. And then what's important is that a cluster can survive n-1 failures, where n is the number of data nodes in a node group. So if we take this setup of a database, for example, then if we lose one management node, then everything is still okay, because we have the secondary management server. Again, if we lose the second management server, still the cluster is operational. And the caveat here is that you cannot do any maintenance, which means you cannot take backups and you cannot join other node groups. Sorry, you cannot join other data nodes, but still your data is available and your cluster is up and running. Then if we start losing data nodes in the node groups, then as we said, up to n-1 in the node group, then the cluster is up and running. So in this case, even though we've lost 4 out of our 6 data nodes, then our data is still there, it's still queryable, and we don't experience any downtime. But we are in a difficult situation here. We have to be careful, because if we lose one more, then we lose all the data nodes in a node group, which means a cluster failure, because for safety reasons, the node group 2 cannot operate by itself. Then we have this the API nodes, which, as I mentioned earlier, they are stateless, even in MySQL. Even the MySQL servers, they are just an interface to RonDB. So they do not store any data. And the only thing that they store is some MySQL specific metadata, such as views. And even the MySQL users, they are replicated and stored in RonDB. And then we have the REST API servers, which again we can have multiple of those, and distributed in availability zone, different availability zones. And again, if we lose them, we don't lose any data, because everything is stored in RonDB. Now, of course, the metadata layer, it's not just a database. We do have the Hopsworks application, which is it's a stateless Payara application server. If you don't know Payara, then it's the enterprise version of Glassfish. So because we offload all the state to RonDB, then it's easier for us to maintain multiple stateless application servers. So we can deploy multiple Hopsworks instances for high availability. And because we don't always want to go to the database, and we sometimes need to take some exclusive locks, we use Hazelcast shared memory for caching and logs. And of course, we run our own Docker registry, and we assume that our customers they have an S3 bucket or an S3 compatible storage, and then we configure the Docker registries to share the volumes in this bucket, so we can deploy multiple registries. So in summary, the metadata layer, we can picture it as this, where at the bottom we have a highly available RonDB cluster, and then we have multiple instances of Hopsworks application server, which are again stateless, so we can deploy as many as we want. Now we move on to our storage systems, and then as I said earlier, we are a dual data management system where we have the online store for low latency and the offline store. So let's explore the characteristics of the online feature store, which basically consists of three main components, and this is a Kafka cluster. Then we have a consumer application, which we call it Online FS, which pulls data from the brokers, and then it stores it into a RonDB cluster. Now, typically, we would have a dedicated RonDB cluster for the online feature store for ease of maintenance and for different SLAs. So at the top, we have a highly available Kafka cluster. There are many resources out on the internet on how to deploy Kafka in high availability. And also in a lot of organizations, there are dedicated teams that maintain their own Kafka. So we can connect to your organization's Kafka. Then the online FS said there are stateless applications, there are Docker containers, and we can deploy multiple of these instances. And in the end, there is the sink, which is the RonDB cluster. And it's a highly available setup again, as I explained earlier. So the only reason, the only place where the online FS interacts with a metadata layer is at the beginning of their lifecycle, and that is to pull the schemas of the topics from the Kafka brokers. So as soon as they have pulled the schemas from the metadata layer, then we can cut the connection and everything will continue to work. So incoming features will be going to online FS and will be stored in the RonDB cluster. Next, we have the offline feature store. The offline feature store is backed up by a distributed file system, which is HopsFS. So HopsFS is our in-house file system, and it's a hierarchical distributed file system. It's POSI compliant, and then it's basically in a head worker architecture. So you have you have the brains of the system, which they're called name nodes, and then the workers, which are the data nodes. If you are familiar with HDFS, then HopsFS, it's a fork of HDFS. The difference is, the big difference is that while in HDFS, all the state is stored in the name node, in the name nodes, then in HopsFS, we have modified the name nodes and all the state is stored in RonDB. What that means is that all the inodes information, all the leases, everything is stored in RonDB. So we don't have a global lock, which is something that Apache HDFS is doing. And then also that gives us the possibility to have multiple active head nodes. for increased performance, but also for higher availability. And then we offload, because every operation in the file system is mapped into transactions in the database. So RonDB supports row level locking, and that way we can offload conflicting file system operations to conflicting transactions, and that way we can resolve the conflicts. So that's what I basically described here. So the name nodes are stateless head nodes. They are the brains of the file system, and they provide information about inodes and files to their clients. And then they also have, being a POSIX compliant file system, we have your regular users, your groups. Users can belong to different groups. Groups can have different permissions. So the names that perform the validation on files and directories, and also encryption keys for encrypting the files in the file system, and general bookkeeping. And then the data nodes, we have for the data nodes, they can store the raw, they store the raw blocks, and they store them in their local hard drive. But also lately we have seen that many organizations either they go on cloud, and in that case they have an S3 compatible storage, which or even if they operate on premises, they do maintain their own S3 compatible object store. There are many of those called, for example, Cohesity, Scality, Mini.io, and what happens is that the data nodes basically they don't store anymore the files locally, but instead they act as a caching layer between the clients and the S3 bucket, which means improved performance because they cache the files. And then, so to recap what we've seen so far, it's we have seen the high availability characteristics of the metadata layer. We've seen the availability of RonDB, the stateless application server. We have seen that we can deploy redundant online FS instances, and also an HA Kafka cluster. And then we went into the offline feature store, where we saw we can deploy multiple name nodes for higher availability, but also for higher performance, and then multiple data nodes which act as a caching layer for your S3 compatible object store. Now we will move to the third part of this webinar, which is the multi-regional availability. So for some systems are mission critical, real-time systems, and downtime is not really an option. Because if there is downtime in these systems, then there are regulatory penalties, and in fact, in some verticals, it's a regulatory requirement. Here, it's a regulatory requirement that you have data replicated in multiple regions or in multiple data centers, to be more precise. And you can see the multi-regional replication as an additional system backup, which is always on. And also the advantage that you have is that there is an instant failover in case of a catastrophic failure of your site, and then that gives us a lower RPO and RTO. So Typically, when you architect different systems, you start questioning whether you want to go active-active or active-passive, and the consensus here is that active-active systems, whilst they provide better characteristics, it's often quite hard to achieve, and not always it's desirable, or not always is a requirement that your system is active-active or the components are active-active. Whilst on the other hand, we have the active-passive systems, where in some cases it's easier to implement and easier to maintain, but sometimes it's not really enough. For example, in the case of in our feature store, in the case of the online feature store, then active-passive, because it serves real-time applications, active-passive is not really an option. We have to be active-active. So Hopsworks is has a modular architecture where you can plug in your own components. For example, you can bring your own Kafka. If your organization has a dedicated team for managing Kafka, then we are happy to integrate with Kafka, with your Kafka. But also, it is architected in a way where, as I showed earlier, we can have different requirements or relaxed requirements for certain parts of our system which are not really mission critical. And that means that, for example, the offline feature store, which usually serves batch inference, batch training, it doesn't have to be necessarily 24/7 up, and we can have it as an active-passive. But before going into details of how we implemented our multi-regional replication, you could think that, so since you store all your data or your metadata in RonDB, why don't you have an additional node group or additional nodes in other regions? Well, the problem is that RonDB internally, it uses a non-blocking two-phase commit, which means that if a transaction takes too long to be committed, then the transaction will be aborted. It will not just stay there hanging. The problem here, and in many, it's a fundamental problem in distributed systems when you have an unreliable network, is what does it mean too long? Is it because there is really a network failure, or is it because there is something jamming the network and will come back again? So for that reason, we cannot just deploy another data node or in another region, and we opted for certain use cases, we opted for asynchronous replication. So the way it works is that so in our RonDB cluster, we have a sidecar process, which is a MySQL process, which continuously replicates the bin log to the other side. So whatever you're writing in your primary region, it will continuously be replicated on your standby region. And for safety, we have multiple replication channels, but only one is active at a time. But there are systems in place where they automatically detect a faulty replication channel, and they automatically take over. Like the standby channels will automatically take over. That means that intra-region, we have a consistent, we have ACID transactions, we have a normal SQL database, which is synchronous and durable, but we asynchronously, we replicate your data into your secondary region. So we can visualize this architecture that I just said in this diagram here, where on the top we have the primary side, which is for simplicity here, have one management node, and just the data nodes. And there is a replica of this site in the replicas of this cluster in the replica site. So you can see that there is replication happening between the MySQL replication servers, and only one active channel at a time will replicate your data on the other side. And then we do have systems in place where they constantly monitor the replication, and they are ready to take over for the backup channel to take over in case of the active replication channel fails. And of course, monitoring alerts. And in more extreme scenarios, we do have also conflict resolution systems in place in case of an active-active replication. Now, going back to our first component that we started investigating, it was the metadata layer. So the way we architecture the metadata layer for multi-region setups is that we have again the host application is stateless, so we deploy as many of them as we wish, and then we have the RonDB cluster on the primary region, which is constantly replicating on the replica region on the right. And all read requests, they are served from your home region, while what's important here is that all the write requests, they are transparently forwarded to the active region. So what that means is that if for example you create a new feature group in the replica region, because there is a load balancer on top of this, there is a load balancer, and you might end up in either of those. So then if you create a feature group on the replica region, then you will transparently be forwarded to the active region, and your client will not notice it. But in the end, the metadata will be replicated on the replica region on the right because of the asynchronous replication. Now, for the online FS, there are different setups that we have considered. One of our biggest customers, they, again, I said, they have their own Kafka team. So they're using the enterprise Kafka, and one of the features is the globally replicated Kafka. I think they call it stretched Kafka. In case you don't have a stretched Kafka, then there are solutions such as Mirror Maker, which will, as the name suggests, it will mirror your brokers to the other region. So we have a stretched Kafka cluster on both regions, and then our online FS application, they push the data to their own disjoint RonDB clusters. So what is important here is that this setup is active, and there is no replication happening between the clusters. The two RonDB clusters, they don't know each other. So we don't need to do any conflict resolution, because and the source of truth is the Kafka topic. And so as I mentioned earlier, the online FS, they contact the metadata layer for some additional metadata, and one of them being the schema of the Kafka topic. But also we store for each topic we store in the RonDB cluster. For each topic, we store the offset of that we last consumed. So each region can consume at its own pace from the Kafka cluster, as long as we are they can be it's fine if there is downtime, because the Kafka brokers will store the incoming events. And it's okay to have downtime as long as our downtime is less than the retention period of the configured Kafka brokers, because after that, then the events will be purged. Now, for the multi-region setups, we need something that tells which regions should be active and which regions should be standby in case of our active and standby configuration. So this service, we call it the active cluster arbitrator, which is basically in computer engineering it's called Oracle, but we didn't want to confuse people with the Oracle. So it's an Oracle. We decide which region is active and which is passive. Again, there are multiple setups you can have in this. The simplest would be multiple HTTP servers, and the only requirements from our systems is that the advertises information in the form of a JSON object. So the simplest setup is you have multiple HTTP servers and then a load balancer in front, and our services they query the load balancer. So and the configuration of which is active and which is the secondary, then it can be automated. But what we've seen from our experience is that usually people want to have it to be a manual process. They just want to be so the failover is automatic, but the act of failing over they still want to be a manual process. So for the offline, moving now to the offline store, then as I said, it's an active passive setup because there are not high requirements for the offline storage, and every service in the offline feature store, it consults the active cluster arbitrator, and if it sees that it should be active, then it remains running. Whilst if it sees that it's in the secondary region, then it dies, and then it tries again after a while, and if nothing has changed, then it will die again until somebody toggles this configuration and makes a failover, where the systems on the new primary region, they will see that they should be active, so they will start automatically, whilst in the replica region, they see that they are the new standby, so they will die. Now, the metadata for the offline feature store, as I said earlier, they are stored in RonDB in the metadata layer, and as we've seen previously, the metadata, the RonDB metadata layer is asynchronously replicated on the passive region. So when the passive region becomes active, it has all the metadata available. Now, for the actual storage of the blocks, as I said, we rely on an S3 compatible object store. Now, if it's on the cloud, then we support all three major cloud providers, and that is AWS S3, the GCS, and the Azure blob storage. But what we have also experienced that all our customers, one way or another, they do have their own S3 compatible object store, and Hopsfs is as long as it has the same API as S3, then Hopsfs can use it as a backend storage engine. So in summary, the offline the offline feature store, the architecture is something like this, where on the left we have the primary region, where we have in the middle we have the name nodes, and they store the metadata information on the RonDB cluster. And then every block is stored in the data nodes, which eventually it end up in the stretched S3 compatible object storage. Now the data nodes, just to remind you that they act as a caching layer. They don't really store any files. So all metadata operations, they end up in the metadata layer, which is asynchronously replicated on the standby region on the right. So if the active cluster arbitrator in the middle, it decides that the standby region should become the primary now, then all the services on the left will automatically shut down. All the services on the right will automatically start running. The metadata are already there because of the asynchronous replication. And then the actual data, they're also there because the object storage is a stretched storage. And with that, I conclude this webinar and the presentation of the high availability characteristics of Hopsworks Feature Store. And if you have any questions, I can take them in the Q&A section here on Slack, or you can join the Hopsworks Slack channel.